I'm Alex. I'm architect in Mellanox Technologies. My presentation is titled Ubiquitous RoCE, and I'm going to talk about deployment of RoCE in large-scale data center networks. So recently, RDMA becomes a crucial technology, and people want to deploy it also in data centers. So RoCE was started as lossless network. This is due to the InfiniBand legacy. InfiniBand assumed that the network is lossless by definition. It's because the InfiniBand was designed for peak performance, and when we drop packets, we waste bandwidth, and we require complex handling of packet retransmission. So already today we have a large deployment, large installation of RoCE in a data center, but it's over a lossless network with our ConnectX-3 cards. And the lossless networks is implemented in Ethernet using priority flow control. That is work as depicted on the figure. So priority flow control is link-based flow control. So when one switch sends packet to the other switch and overflows the switch buffers, the other switch, here the switch on the right, will send back a pause frame to indicate the switch on the left to stop sending packets. And when the buffer is empty, the switch on the right will send another packet, which is called unpaused packet, to indicate to the switch on the left that it can continue to transmit packets. So this is how the priority flow control is used in Ethernet. In InfiniBand, it's a slightly different scheme, but essentially it provides the same results. However, data center networks traditionally use Ethernet, and the operators don't like lossless network. They prefer lossy networks for several reasons. One of them is because it's easier to configure lossy networks. You don't need to define priorities. You don't need to classify traffic to priority. There is no need to set different types of thresholds, and etc. There are also, today, the routing algorithms in Ethernet may cause to a phenomena that is called PFC deadlock, or credit loops deadlock. Moreover, data center networks are usually less plans, and their application traffic is less network friendly, and there may be more legacy reasons. So this is why users don't want to deploy flow control, so we need to deploy congestion control. So contrary to lossless networks, the congestion was not a killer because of the flow control. And in lossy networks, when congestion happens, like in this scenario, the packets are dropped. So here we see 3 hosts that are sending to the common destination. And after some short time, the switch buffers will overfill, and packets will be dropped in a continuous and high rate. So congestion control works end-to-end, contrary to the flow control, meaning that the rate of the traffic injectors is throttled. So perfect congestion control, what it aims to achieve is to reduce the queues length in the congestion point and the switches, keeping the high bottleneck link utilization and fairness between the senders. So here, in this simple scenario, the congestion control will achieve that each of the hosts will send on the rate that is equal to third of the link rate, such that the bottleneck link will be utilized and not overutilized. So luckily, we have congestion control algorithm for RoCE. It is called DCQCN, which is abbreviation for data center QCN, which is in turn short for quantized congestion notification. And it is based on a combination of previously known algorithms, DCTCP and QCN. This algorithm was developed in collaboration with Microsoft, and it was already documented, and its details were published in a paper from SIGCOMM conference in 2015. It is also initially implemented in ConnectX-3 Pro cards, but it is firmware-based implementation. So in next slides, I will briefly explain how this algorithm works system-wide. So RoCE packet format is basically an InfiniBand packet which is encapsulated in the UDP header, IP header, and Ethernet header. For the congestion control, we use ECN fields of the IP header to mark the congestion. So the congestion point, which is the switch, the congestion switch, marks the ECN bits of the RoCE packet that traverse to it based on the queue length. When queue length of the switch reach some threshold, meaning there is congestion over this queue, the packets are being ECN marked based on some probability. And this is standard functionality that is supported in all commodity data center switches, Ethernet switches. Because it initially was designed for TCP. It also can be used for TCP, given the host supporting this functionality as well. So the marked packet, the packet is marked in the switch and traverses the receiver NIC, which is called notification point. The notification point in its turn, when it received RDMA RoCE packet with ECN marked, it will create a send CNP, which is congestion notification packet, back to the sender to indicate about the congestion on the route. In ConnectX-4 card, the CNP generation is implemented by NIC hardware, which provides very fast response from getting the ECN marked packet and sending and sending the CNP. An additional attribute of CNPs is the ability to assign a specific different priority to CNPs rather than to data packets, and with appropriate end-to-end quality of service configuration in the network, it can be also be delivered on the fast guaranteed service paths with low latency, such as can bypass the congested queue in the network. So we can generate packets, CNP packets fast, and transmit them to the other side of the network fast. So reaction point, which is the NIC that's sending the congested traffic, it simply receives the CNP packet and throttles the sending rate based on the rate of the arrivals of CNPs. There is some more complicated algorithm that I will not explain here, but it is documented and it is based. Most of it is based on the definition of QCN. In the future devices, we also plan to throttle the rate based on the packet drop. Packet drop is usually indicated by receiving of out-of-sequence snack. But today it's still not supported. When it will be supported, we will not require a ECN marking, ECN feature from the switches. So it will even be very easier to configure. And reaction point is also implemented by ConnectX-4 hardware, which also allows fast response to the congestion notification. So the big novelty here is the hardware-based congestion control that is implemented in ConnectX Arba, and it allowed to Mellanox to announce resilient RoCE. Resilient RoCE means that now RoCE can run over lossy network. We do not require flow control. We do not require lossless network anymore. And the reason for that is that hardware-based congestion control is much faster than software-based implementations. For example, the reaction point can react in orders of time of tens nanoseconds from the arrival of CNP and to rate reduction, compared to the software or firmware-based implementation that it took tens of microseconds and even more to react. So there are several orders of magnitude difference in the reaction time. And fast reaction time to the congestion minimizes the network congestion time. It means that now it is less likely that the congestion switch buffers will overflow. So we drastically reduce the probability that the packets will be dropped or the buffer will overflow. Still, congestion control does not prevent drops at all, contrary to flow control. There might be cases of very stressed traffic or some very temporal scenarios of bursts in which packets are dropped. And here we rely on the InfiniBand transport semantics to cope with the packet drops. So So InfiniBand transport is reliable by definition. It is sold under InfiniBand certification. And it works in this way. So the requester sends packets to the responder, and the packets are marked with sequence number. Sequence number, shortly, it's called PSN. The responder tracks the sequence number that arrives. And on the first packet of each flow, of each QP, that arrives out of order, meaning the sequence number are not continuous, it creates and sends a message or packet that is called out-of-sequence NAC. When the requester receives out-of-sequence NAC, this out-of-sequence NAC includes the PSN, the sequence number of the packets that was expected and was not arrived. So when the requester receives out-of-sequence NAC, it simply retransmits the packets, again starting from the packet that was expected and indicated in the out-of-sequence NAC packet. So previously, since RoCE and RDMA were assumed lossless networks, so drops were assumed to be very rare. So previous devices, the handling of out-of-sequence packets was relatively complex and slow. And today, in every ConnectX device that Mellanox designs, in every generation, we have better implementation, better semantics, and we add layers of hardware acceleration to handle better with packet loss. But basically, this is how the scheme works today. So, as I said, resilient RoCE, meaning that now we do not need to configure flow control to make RoCE work in scale. So basically, we can say that RoCE works out of the box. And the only requirement is to set SCN thresholds on the switches, because this is essential part of the congestion control algorithm. However, as in everything that we do, if we want to achieve the peak performance, we still can have some features that provided by a network, by Ethernet network, in which we can still improve the performance. So each additional layer of the quality of service configuration will improve the performance, as listed in the next examples. So as I already mentioned in one of the previous slides, one of the suggestions is to set the CNPs, the congestion notification packets, to high priority traffic class with assured buffering and scheduling. And this we can make fast propagation of the congestion notification from the notification point to the reaction point. And that's allowed by passing the congested queues. Next recommendation is to isolate RoCE traffic from the other traffic that exists in the network. For example, large-scale data center may have another traffic, significant traffic, TCP or UDP. And coexistent with them might harm the performance of RoCE. So for UDP traffic, it is trivial. UDP traffic is not congestion control. So if in case of congestion, we will have backoff of RoCE traffic, but not backoff of UDP traffic. But even if the other background traffic is TCP, it usually has different congestion control scheme, and it can have different implementation. It responds slower to congestion compared to RoCE. So if we want to bring the RoCE performance to the peak, we can assign RoCE traffic to a different class. And again, with guaranteeing buffering and scheduling. And lastly, we can also still use flow control to really achieve the peak performance, because we still believe that it's better to pause packets than drop packets, because dropping packets has some time to sender to understand that packet was dropped, and it required to retransmit it. So usually it's better just to pause the link and not to drop the packets. So this is to achieve, those are the steps to achieve the peak performance. So in the second part of the presentation, I have a bunch of slides that shows the lab experiments that we did with different scenarios and different network configuration. And using these slides, I will try to prove that what I said in the first part is actually true, and we can also achieve fair and good performance with resilient RoCE. So this is the lab setup that we used for our testing. Usually have two clusters. One which we call small cluster. It is combined from 17 hosts that are all connected to a single switch in the star topology. And it is used to mimic single rack traffic. The second lab setup is what we call large cluster. It is combined from 64 hosts, divided into 2 groups, and connected with 3 switches between them, where there are multiple links between the switches. This is used in order to mimic inter-rack traffic with multi-paths between them. So the traffic patterns that we run, we run many-to-one traffic pattern, which is the classical scenario to test congestion control algorithms. In this case, all the hosts are sending traffic to one host, making the link toward one of the hosts as congested as possible. The other traffic pattern is all-to-all. In this traffic pattern, every host sends traffic to every other host in an equal, uniform way. So we also tested several traffic configuration with traffic network configuration. So we began from RoCE over lossless networks to use it as our benchmark. We continue, of course, to test RoCE over lossy networks. We tested coexistence of RoCE with TCP traffic with configuration of network as I served previously, with priority separation between RoCE and TCP. And we also tested RoCE and TCP combined on the same network without any configuration of priorities. And we also have a test of TCP only to compare how resilient RoCE is, to compare it to resilient RoCE. So there are more details about the test on the slide. I will skip them, but you can read from the slide. So the first scenario is the simple and the most simple scenario. We begin with a small cluster running many-to-one test over lossless network. So we have 16 hosts are all sending to a single host. And each sender, each one of the 16 hosts, also opens 64 flows, 64 queue pairs toward the receiver. So we have in total 64 multiplied by 16 queue pairs running toward a common receiver. So we see the results on the graphs below. The left graph shows the total throughput that arrives toward the receiver. And of course, it's not surprising, since this is lossless network, we can see throughput that is almost equal to the link rate. The graph in the middle shows throughput per sender. So there are actually 16 graphs that overlap one over the other in this figure. And this indicates that there is a fair distribution and stable rate between all the senders in this test. And lastly, the graph on the right shows the pause duration on the host. So the switch, when its buffers gets full, it sends pauses to the host, and we sample the counters of the pause duration that each host, the time that each host is paused for sending the traffic. So in this graph, we can see that in the beginning of the test, when we begin to inject the traffic, there are short period that congestion control converges, and then there is no pauses during the test at all. So it takes some time to congestion control to converge, but even these times, it only occurred 0.35% of pause duration in the very first second of the test. So it's very short convergence times of the congestion control, and we basically believe that since we have hardware-based congestion control and the network is lossless, it's probably the best time that can be achieved. Next, we tested the same scenario over the lossy network. So this is when the interesting test begins. So this is completely the same scenario, 16 hosts, each one with 64 QPs are sending to the same common destination. So as in previous slide, we got perfect total throughput, perfect throughput per sender, meaning that there's fair rate distribution between the senders. And the difference here from the previous slide is the right graph. So now we do not have pause duration because this network is lossy. So we can count the out-of-sequence events that each host sees. out-of-sequence event indicates packet drop. So as previously, we see some time that it took the congestion control to converge. So we see some packet drops in the beginning. But here the most interesting conclusion from here is that even giving packet drops, RoCE works. So drops do not break the performance of RoCE, which is important proof to announce for a resilient RoCE announcement. Next, we did this test. We repeated this similar test, which a little harder, make the system a little harder. We stressed the system with a very large amount of QPs. So here we have still 16 hosts, but now each host creates and sends 512 QPs toward the destination. So here in this case, the congestion control could not converge well, and we see the graph on the right side that we still have packet drops during the test. And what is interesting that the total throughput on the graph on the left is still achieved. It still remains on the maximum level, and this is despite the losses that the packet drops that happen. We still have some unfairness between the senders that are indicated in the graph in the center. So we still have where to improve in our next releases, software and hardware. But still, the conclusion here is that given continuous drops, RoCE can transmit packets. So flows do not break, and data is continue to stream to the receiver. Now, it was interesting to compare RoCE to TCP in the congestion scenario. So we repeated the same case, one experiment with TCP and second experiment with RoCE. So I already saw the graphs for RoCE. It is not surprising that we are getting full throughput and full fairness and negligible CPU usage. It is shown on the 3 bottom graphs. And it is interesting to compare how it compares to TCP. So the upper graph shows the results for TCP. We can see that total throughput for TCP is not stable, and in average it is around 60% of the total throughput that can be achieved. Also, the throughput per sender is very fluctuates, and it's less fair specifically compared to what we achieve with RoCE. And the CPU usage on the receiver node was utilized almost 50% of the time only to handle this communication. Again, with negligible CPU usage on the RoCE side. Next, we tested hybrid traffic of coexistence of RoCE and TCP together on the same network. So first, we began with setting priorities. We isolated two types of traffic to different priorities, as I said previously. And we have 16 hosts sending to one receiver each. And we have RoCE QPs and TCP flows streaming from the same host to the same receiver. So the upper left graph shows the total throughput of both RoCE and TCP. And we see that giving the priorities isolation, RoCE usually achieves at least 50% of it, almost achieves 50% of the times, 50% of the throughput all the time. There are some dips in the throughput of TCP, probably because of the underutilized queues on the congestion switch of TCP. So this is because of the TCP behavior and not because of RoCE or the configuration. We see some pauses in the beginning of the test, but we already saw it in the previous slides. What's also interesting that interflow fairness in RoCE is preserved perfectly, and the TCP has some unfairness between the senders of TCP. So now it will be interesting to repeat the same test, but without the priorities configurations. So in these slides, we remove the configuration. So now TCP and RoCE runs on the same priority. Here we have the same setup, but now we have 64 QPs of RoCE and 32 flows of TCP running to the same destination over a lossy network. And the left graph shows the throughput of RoCE and throughput of TCP. So RoCE usually achieved, it is not stable as was previously, of course, but it has achieved above 60% of throughput for RoCE and around 30% of throughput for TCP. And it's interesting that it is it was good finding that we see that it is close to the ratio between the number of flows. So we have 2 times more flows of RoCE compared to flows of TCP, and also we get 2 times more throughput of RoCE compared to TCP, and this without any configuration of scheduling. So the graphs of fairness of throughput per sender are also not stable as previously. It's because the TCP traffic sometimes harms to traffic of RoCE, but still we can say that these results are pretty good. So here this is RoCE that run on lossy networks with significant background TCP traffic, and still RoCE flows continue and keeps with high throughput. In the all-to-all scenario, so as I said previously, in all-to-all scenario, every host sends traffic to every other host. This is interesting scenario. In average, we should not see any congestion, but because of the burst and desynchronization of the sender, the switch buffers are still getting full. In this case, the congestion can harm the system, so it is interesting to see in this case as well. And the slide presents results for lossless and for lossy network. So for lossless network, we achieved perfect results. For lossy networks, we were relatively close to perfect results. Next, continue to the large cluster testings. So here we have much higher stress on the network and on the congestion control algorithms. So we have 63 hosts that were sending to continuous loss to one destination. We have 16 QPs per sender per every host. And this graph combines the results of lossless network and results of lossy network. So the graph on the left, the bottom left graph shows the total throughput of lossless and of lossy. They slightly overlap one over the other. It means that the throughput of lossy is almost equal to the throughput of lossless network. The graphs on the middle shows throughput per sender to that indicate the fairness between the senders. So of course for lossless network we already know we get full and perfect fairness. For lossy network it is slightly not so fair, not so stable. But again the major point is that the total throughput remains fair and stable. Lossy is very close to lossless. Now the scenario of all-to-all. So here 64 hosts are sending traffic. Every host sends traffic to every other host. And we see that both in lossless network and in lossy network, we again get almost full link rate, throughput of almost full link rate. Lastly, in the last experiment that I will show in my slides, we compare RoCE to TCP over the large cluster. This is many to one scenario. Again, we repeated the same experiment for RoCE and for TCP. So we already know the results for RoCE. The same scenario for TCP, we show TCP achieves only half, the throughput is achieved only half of the link rate, as it's indicated on the upper left graph. And the upper right graph shows the CPU load, and we can see that the receiver of TCP traffic is 100% is utilized. So this is probably why it cannot achieve higher throughput in the network. So to summarize, many data center users would like to deploy RoCE using lossy network due to several reasons that I mentioned at the beginning. And recently Mellanox announced the resilient RoCE, which means that now we can run RoCE without flow control, meaning over a lossy network. This was allowed by implementation of the congestion controlling hardware of ConnectX 4. We still, as I surveyed in the presentation, in order to achieve the maximum of the peak performance, we have some tools that are provided by quality of service of Ethernet network. And I showed many lab measurements of different types of traffic, lossless, lossy, with different scenarios of many to one, all-to-all. And we showed coexistence with TCP and comparison to TCP. And major conclusion from this presentation is basically that resilient RoCE works. Thank you.
I'm just curious, if you could go back, I don't know, half a dozen or so slides to the small cluster with lossy enabled. It shows RoCE being very fair between the senders, right? It doesn't seem to show...
This one, right?
Yeah,
This one.
Small cluster lossy. One more earlier. The sort of, yeah, this one. So it almost looks like the each sender is not hunting much at all for sort of the optimal throughput rate, and I'm not sure. It doesn't make sense to me exactly how that can be accomplished, right? There's no global coordination. It seems like each one is individually being throttled via ECN when the switch buffers fill up. And I know it's probabilistic, but I would expect to see a little more hunting along the lines of TCP. And it's not clear to me what part of the system is providing that dead solid smoothness.
So this is the attribute of the algorithm of the congestion control. TCP usually throttles back the rate by reducing the rate to half.
Mm-hmm.
Okay, every packet when packet drop is identified, the sender throttles the rate by half. Here in our algorithm is more accurate. I can give you more details on. There's also documentation, but basically we maintain some parameter that we call alpha, and alpha is estimation of the congestion in the network. And when the network is not very congested, so the rate is reduced by some by ratio of this alpha. In alpha, it's not always half. It can also be like 10% or 5% of the network. So we not always throttle the rate by half. This answers the question, and this makes the graph looks more stable and not like in a sawtooth of TCP.
Okay, thanks.
So you probably have some counter for getting the out of sequence.
Sorry, I couldn't hear.
So you probably have some kind of counter that gives you the out of sequence packets, right? You showed those things where you...
Yes.
So one question I had was, for the first OOS packet, you sent back something like TCP's DoPack. You sent back that NAC, which says this is the sequence number 1.
It's called out of sequence.
Right.
Yeah.
But that could just be packet reordering in the network. So in TCP, you wait for 3 DoPacks before you do a fast retransmit. Why do you do a fast retransmit immediately? I mean, couldn't it be that everything's just coming and you just got it from order?
The TCP waits for 3 DoPacks from the reasons of packet reordering in the network. Sometimes the out of order arrival may indicate different parts of their network. This is the case that is true to global internet. And TCP becomes first it was established in the global internet, so where packets can take several routes. But at least today in Datacenter Networks we use CMP, so every flow runs on specific paths. So we don't have reordering inside the network.
The routing table could still change. Right?
This is why we can the first out of order arrival indicates packet drop and not reordering. So we can immediately retransmit the packet.
Okay, but if you have ECMP and routing table changes, this could still happen, right? I mean,
it's
possible.
ECMP maintains ECMP maintains the flow order because it works on the 5 tuple of it works on the 5 tuples. So every 5 tuple, every flow will always take the same path in the network.
Okay.